Dear students, welcome to the lecture on optimal control 1. In our previous lectures, we have seen various aspects of control systems, namely the controllability, observability, stability aspect. So, mainly we have seen linear control system of the form dx by dt is equal to ax plus bu with initial condition x of t naught equal to x naught, x of capital T equal to x1. So, in this case, if the system is controllable, then we will be able to find a control u of t given by this expression B transpose phi transpose T naught t and W inverse into phi of T naught capital T x1 minus x naught. So, if the system is controllable, then this control u of t will be able to steer the system or steer the solution x of t from the initial condition x naught to the final condition x1 at time capital T. If here the W, the notation W, it is nothing but the controllability Gramian matrix which was described in the previous lectures, and if W is non-singular, the system is controllable. That is how we will be able to find this control like this. Apart from this particular control, there may be several other control functions which can perform the same type of work, that is taking the system from the initial condition to the final condition. So, there may be several such controls and there may be several solutions for this control system. So, if let us say V of t is another control, which steers the system, steers x of t from x0 to the x1 in the interval t0 to capital T. Then we have also proved that integral t0 to capital T norm of u t whole square dt, it is less than or equal to t0 to capital T norm of v t into dt. So, in the sense that if you take any control which is steering the solution from x0 to x1, the control given in this particular expression has the lowest value for this integral. So, if you call this j to be this expression, so j the minimum of j which is equal to integral t0 to capital T of norm of v t square dt over all t, over all functions v, all possible control functions v. If you find this minimum value, that will be equal to this j value expression, this thing, or in other words we can say that the control given in this expression minimizes the functional j which is given in this expression. The functional j is integral t0 to t norm of v of t square dt. The minimum value of this functional is given by the control u of t. So, now this is one particular case of a optimal control problem. So, in general the optimal control problem is given by, we consider a control system x dot equal to x of t u of t. Let us say nonlinear control system is given by this expression, which such that the cost function between some 2 times of a expression x of t u of t dt is minimized. So, the optimal control problem is as follows. We have a control system x dot is equal to f of x of t u of t such that the cost functional j is minimized or optimized, minimized or maximized according to the statement of the problem under suitable boundary conditions. So, in this lecture we will see how to derive conditions or necessary condition for finding the optimal control for a system, a linear system in this expression. So, first let us see the preliminary results which will lead to the necessary conditions. So, it is based on the calculus of variation. Let J be a functional which is to be maximized or minimized, and del J is the notation for the increment of the functional. So, J as we have given, it may be of the form a integral from the interval of a function x of t and x dot of t dt. So, a expression of this form if you consider, then we can find the increment j given by this expression j of x of t plus del x t, which is the variational in the function x of t minus j of x t. So, we, for example, if we consider the time t naught to t is this and x of t is a function between t naught to capital T, then the variation, by adding some variation we will get a new function. So, we call it as x of t plus del of x of t. So, if we calculate j at the function x of t, it will be of this expression, and we calculate j at the incremental function x of t plus del x t, we have to substitute in the place of x the expression x t plus del x t, and then subtract this 2, we will get the increment of this thing. For example, if we consider a expression j as a function of x here, it is integral t 0 to capital T x square of t plus 3 x t. Then how to find the increment of this functional? It is given by this expression, directly substituting x plus del x in the place of x and subtracting j of x directly, we will get the expression. So, the last line we are omitting the second variation, that is del x whole square term is omitted and the remaining term gives the first variation. This is called first variation of the functional j here. Okay. So, here again we calculate the increment of the functional j, del j equal to j of x plus del x minus j of x, and expanding it in the Taylor series, x f j of x plus del x will give j of x plus the first variation del j by del x into the delta x of t plus 1 by 2 factorial, and the second variation etc. minus j of x t. So, that gives the increment, and j get cancelled, we will get del j plus del square j. This is the notation for the second variation, del j is the notation for the first variation, and that was shown in the previous example. This is the first variation, and now see, in the previous case the Taylor series expansion will stop up to the square term, there will not be any cube terms etc., because it is a polynomial of degree 2 here, but in general for any general function we will get all the terms, and then we can calculate first variation, second variation and etc. So, using this first and second variation we can get the optimal value of the functional using the following theorem. So, here we define the j is said to have a relative optimum at a function x star if there exists a positive epsilon such that for all functions x in the domain omega, the neighborhood of this functional neighborhood of the function x star, which satisfy this. So, we take the collection of all functions which are near the function x star in the epsilon neighborhood, and then the increment has the sign, positive sign always, then it is called relative minimum. The function x star is called the relative minimum if the increment del j is greater than or equal to 0, and if the increment del j is less than or equal to 0, then the function x star is called the relative maximum. And instead of the neighborhood, epsilon neighborhood, if it is the condition is satisfying for all values of epsilon, then we say that it is the global optimum, global minimum or global maximum depending on the increment nature. So, then we can the standard theorem on the optimum function is as follows. The function x star t is said to be a optimum function, or it is a candidate for optimum function, because this theorem first statement is only the necessary condition. So, it will be a candidate for optimum function if the first variation of j is equal to 0. So, it is a necessary condition. Then we can confirm whether it is maximum or minimum by the second variation. If del square j is less than 0, then it is the maximum value, and if del square j is greater than 0, it is minimum value. So, even though it is similar to the theorem for functions, here the similar result holds good for the functional j also. Okay. Now, we will come to the result on how to find the optimum function for the functional j. So, let us say j of x is given by this expression integral t naught to capital T capital F of x t comma x dot t comma t dt, with the initial condition x of t naught is x naught and x of capital T is x f. Okay. So, the function has these two fixed boundary conditions, that is from t naught to t, these two are fixed, initial and final conditions are fixed here. Now, because these two are fixed, the variation at the end point is 0, because if you add a delta, this is our x function, and if you add a delta x function, so there is a variation at other points of t. If take general t, there is a variation between x and delta x, but there is no variation at the end point. So, the variation at t0 and variation at capital T both are 0. So, now the way the increment del j is given by j of x star plus del x. So, we calculate the variation between. So, let us say this is our required optimum solution. For example, if we take it as the optimum solution, then the increment is given by x star plus delta x. Now, calculating j value at this and these two functions. So, the increment is j calculated at x star plus its increment minus j calculated at the value at the function x star. So, that is given by integral t0 to t capital F of, we substitute the x star plus del x in the suitable places, minus integral t0 to capital T F of x star and x dot star t dt. Now, we use the Taylor series expansion for the function capital F, term similar to the second f of x star x dot star t is the first term of the Taylor series, which will get cancelled. So, the remaining terms will appear like this. So, the increment j is given by del f by del x into del x plus del f by del x dot into del x dot, plus the second derivative terms are given by this expression into dt. So, the first variation is given by only the first derivative terms here. So, it is del f by del x into del x plus del f by del x dot into del x dot into dt, and we omit all the second derivative terms here. Because of the theorem statement, the first variation, if we equate it to 0, it is a necessary condition for the optimum function condition. So, now if you calculate this term, second term, del f by del x dot into del x dot, we take that term del f by del x dot into del x dot is written as del f by del x dot d by dt of del x, this expression. Now, we can integrate by parts this term, we get del f by del x dot into del x evaluated at t0 to t, the end points, minus integral t0 to t del x of t into d by dt of the first function del f by del x dot into dt. Hence, we get the expression of this form. The first variation in j, del j is given by integral t0 to t of, from the previous slide, this del j is given by del f by del x into dx into del f by del x into del x dt is one term, and this term, second term, is replaced by this expression. So, ultimately we get del j equal to t0 to t del f by del x minus d by dt del f by del x dot into del x dot, and this term is 0 because there is no variation. If you substitute t naught at t, we know that del x t naught is 0 and del x t is also 0 because there is no variation at the two end points, as we have shown here. The del x at t naught is 0 and del x at capital T is 0. So, here this term will become 0. Now, this implies the variation del x is also arbitrary. From this picture we can see that x star is a fixed, it is the function required function, and then we can add any del x function with this, so that we get infinitely many such this type of functions. So, the variation del x is arbitrary, we get this expression del f by del x minus d by dt of del f by del x dot equal to 0, del x t is arbitrary. So, this equation is called the Euler's equation for the minimization or maximization of the functional j here. So, here there is no guarantee that this equation will give minimum or maximum, because it is only the necessary condition. And if you check the second variation, whether it is positive or negative at this solution of this equation, then we can conclude whether the solution is actually minimum or maximum or none of this, both of. So, it gives a necessary, Euler's equation gives a necessary condition for the optimum function. So, now we quickly generalize the previous procedure for two variable. So, j is a function of x1 x2 given by this expression integral t0 to capital T capital F of x1 x2 x1 dot x2 dot into dt, subject to the condition g of x1 x2 x1 dot x2 dot equal to 0 with the boundary conditions x1 of t0 and x2 of t0. Similarly, x1 dot at capital T and x2 dot at capital T, these values are given, the fixed values are given. So, now we can, because it is previously it was one variable, now it is two variable, the procedure is exactly the same, except that we have to write the Taylor series for the two variable and omit the second order terms and take the first variation equal to 0. And the difference between the previous one and here is there is a constraint. the minimization or maximization of j subject to the condition g of x1 x2 x1 dot x2 dot equal to 0. So, this can be done in the usual way of the Lagrange multiplier method, because this is a constraint. So, we define the Lagrange function L of x1 x2 x1 dot x2 dot lambda, which is the Lagrange multiplier, equal to the function capital F plus lambda times the function g. Here g is a vector function, because there are two variable, it may contain two function g1 g2, g1 of x1 x2 x1 dot x2 dot. Similarly, g2 also contains. So, g is a vector function, and therefore, lambda is also having two components, lambda 1 lambda 2, and the transpose is given. So, we get a scalar functional here, L is capital F, which is a scalar function, plus lambda dashed into g, that is also a scalar function. And now we can proceed with this J A. Minimizing J A will give the minimum value of the j itself. Okay. So, to generalize the previous procedure, we take the incremental function, that is x1 star is the required function, and then if we add a variational function delta x I along with that, we get the function variation of x star. Substituting the variation and then subtracting with the original function j a and taking only the first order terms, in this way we get the equation exactly similar to the previous one, and replacing the terms containing dot del L by del x1 dot into del x1 dot. So, if you use the integration by part method as done before, we get exactly similar equation. Instead of one equation, we will get two equation, two Euler's equation, and the constraint function g means the vector g1 g2 equal to 0 is given here. So, the same thing is extended for the general one. If x is a vector x1 of t, x2 of t, etc., xn of t, and its derivative is given, and g I. So, g is g1 g2 gn m. Okay. There are m constraints and n variables are given. So, the procedure is exactly similar, and here the lambda will be simply lambda 1 lambda 2 lambda m dashed, which are functions of t. So, we proceed in the similar manner as we did earlier, and we get the Euler's equation for the n Euler's equation will be obtained, and the m constraints are already given in the thing, and the initial conditions and final conditions are taken as in the previous case. Here we have given. So, initial and final condition for two x1 and x2 are given. Similarly, we can take the fixed initial and final condition for n such functional. So, now we will use this procedure to solve the optimal control problems as follows. So, for example, if you consider the equation x dot is equal to 2x plus 3u, and we want to minimize the functional, say 1 to 5 of 5 x square plus u square. These are functions of t dt. Okay. We want to minimize this expression under the condition, say x of 1 These are the boundary conditions. X of 1 is 0 and x of 5 equal to 4. So, the equation is given, the constraint equation is given, the first one, and the functional to be minimized is given, and the boundary conditions are given here. So, we can construct the Euler-Lagrange equation as given here for the one variable case. So, we have to construct the function L. L of x dot lambda is given by f function plus lambda times g function. So, this two we will construct here. So, here the function f of x of t and u of t is given by 5x square and u square. So, this function and g of x comma u, x of t, u of t is given by 2x plus 3u minus x dot, is not it, because g of x u should be equal to 0, that is given from the equation 1. Then the Lagrangian is given by, the Lagrangian is a function of x, x dot and u, that is given by capital F plus lambda times the function g. So, if we take this one, we get 5x square plus u square plus lambda times g function is given by 2x plus 3u minus x dot. So, the Euler's equation is Euler-Lagrange equation is del L by del x minus d by dt of del L by del x dot. See, here we note that this problem j of x1 x2 is given by integral f of x1 x2 x1 dot x2 dot, that is to be minimized. So, now we can take in this problem x and u are there in our statement of the problem. J is 5x square plus u square. So, we can take this x2 function, x1 as x here, x in that problem, and x2 as the u, the control u, and g of x1 x2 x1 dot x2 dot. So, x1 is replaced by x here, x2 is replaced by u, and x1 dot is replaced by x dot, and u dot is not available in the equation. So, we can simply write the expression like this. So, g of xu we are writing instead in the place of x1 x2 we have x and u, and this expression is given, x and x dot also. So, we have this expression, and we can write the Euler's equation like this with the initial condition given, initial and boundary condition given by 3, and del L by del x2, in the place of x2 you have u here minus d by dt of del L by del u dot. So, these are the equation to be solved, and we get del L by del lambda, that is equal to g, which is also equal to 0. So, this equation to be solved. Now, directly if we differentiate del L by del x etc., we will get the equations in this form. So, this implies del L by del x, from here directly if we differentiate we will get 10x plus 2 lambda minus d by dt of del L by del x dot, there is a x dot here. So, it is minus lambda equal to 0. So, from the first equation we get this implies equal to lambda dot, the derivative d by dt of lambda, and then del L by del u. If we differentiate with respect to u in the second equation, we get 2u and minus del L by del u, that is plus 3 lambda. So, that is equal to 0. So, this equation implies that u equal to minus 3 by 2 lambda. So, we get this as the first equation and this as second equation. The third equation is already given, g equal to 0, that is the given constraint, that implies x dot equal to 2x plus 3u. So, this is the third equation. So, combining all this equation we get, so now we have to solve the equation x dot equal to 2x plus 3u from third equation. The first equation is lambda dot is equal to u is equal to minus 3 by 2 lambda. If you substitute u in this expression, we will get 2x 3 by 2 lambda. So, we will get 9 by 2 lambda. So, we have made use of all the equation. This is the expression with the boundary condition x of 1 equal to 0 and x of 5 equal to 4. So, this is a system of equation. We get x lambda. If you write in the matrix form, this equation will give 2 minus 9 by 2 and lambda dot is 10 and 2 x lambda. So, we get the matrix equation in this form. By finding the exponential of this matrix, we can find the solution of this problem under the boundary condition here x1 of 0 equal to 0 and x5 of 0, x5 equal to 4. So, with this we come to the conclusion of this lecture. We have demonstrated how to find the optimal control for a linear system with the fixed boundary conditions, and but this procedure is not restricted to only linear system, because the equation given in the procedure which we have explained earlier, it is the constraint is given by g I of x dot equal to 0, which can be a nonlinear system also. But in this particular example, we have taken the linear system because the solution of the linear system can be obtained analytically and the result can be obtained analytically. Otherwise, the procedure can be applied for nonlinear system also. Thank you.